Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a specific part of the concept of calculus that we talked about. Of course, we have seen an introductory part in our first videos that we did. So today we are going to look at the concept of an integral. And specifically, we're going to look at the area beneath a curve. As we said, this concept of calculus is very important in trying to determine the area that is bound by curve. So for that case, thank you and welcome. So as I've said, today we're going to look at the concept of integral, and we're going to see that this concept of integration, of course, is very much important in determining areas that are bound by curves. So this the concept of areas, of course, this is integration aspect of calculus, integration, and in this case, as I've said, we're going to look at the area that is bound by curve. Now, as we generally said, the concept of integration arose from the fact that initially people used to do surveying and calculation of areas of land by the use of regular figures that we are familiar with, of course, like the squares, the concept of finding areas of the squares, rectangles, triangles, and partly circles. So these are some of the areas that were used, of course, in determining areas of maybe in the concept of doing surveying or maybe trying to calculate the areas of land. And in that case, of course, there was a use of different concepts for regular figures, the common regular figures that we know. Maybe if the area was in form of a rectangle, then they could just do length times width, and this is half base times height, and then pi r squared, and this is the length times length, or maybe side times side. So in that case, these were the main concepts that were used. But of course, when it came to areas whereby maybe this is a piece of land A, and then this is a piece of land B, and for a piece of land C, and then if we had a piece of land that had maybe an irregular figure like that, it was very much challenging because these methods of trying to do calculations were quite cumbersome in trying to find out. Of course, there was a use of circles in this case, which was the simplest form that they could find, since it has some aspects of a curve. And then this use of this circle was due to the fact that, of course, there was a known relationship that existed for the ratio of the area of the circle. This is the area of the circle over the square of the radius. And then if we try to write for these symbols, and then we shall have this one. That one gives us a concept of a familiar formula that we are aware of. Of course, I've talked about the circle, whose area is given us by r squared. So the ratio between area and the square of a radius gives us a constant, which is a common constant that we normally call, of course, pi. So in this case, this concept was very important in trying to assist them figure out, and it was only successful in limited cases. So in that case, of course, they had to find a new way of trying to find areas, or maybe how to figure out areas of curved surfaces. Now in this case, mathematicians became concerned by this kind of curves, and then later on they used the concept of one of the scientists, of course, who had proposed some methods of trying to figure out or to find the relationship between areas that had curved surfaces and the relationship between the aspects of these regular figures that we have talked about and the curved surfaces. Now, the name of this was in the early 17th century, whereby Johannes Kepler came up with a second law of planetary motion, which states that the speed of a planet in its orbit varies in such a way that a line joining the planet So Johannes Kepler's argument was that the speed of a planet in its orbit varies in such a way that a line joining the planet to the sun sweeps out equal areas in equal period of time. We shall use a demonstration to try and write or just demonstrate the argument of Johannes Kepler that the speed of a planet in its orbit varies in such a way that the line joining the planet to the sun sweeps out equal areas in equal period of time. So you can see this concept of equal areas and equal period of time. Now in this case, if you try to elaborate Johannes Kepler's second law of planetary motion and try to see the relationship that he was trying to develop, that maybe which subsequent scientists used to come up with the concept of finding areas of curved surfaces. Of course, we know that planetary orbits, like the orbit of the Earth, which goes around the sun, goes in circular motion. Of course, we shall just use that demonstration, and suppose this is the position of the sun, and then this is a planet that is revolving around it. So you find that maybe for that planet, as it goes around the sun, for it to move from point A to B, now Johannes Kepler's argument was that these lines, let's denote it by just R, not indicating radius, but just R, letter R, to differentiate between these other symbols. So for the line R, if this planet moves from this point A to B, this line will have swept the area that is shaded as I've done. So in that case, you'll find that this argument was the speed of this planet as it orbits varies in such a way that a line joining the planet to the sun sweeps out equal areas in equal period of time. So suppose the planet in moving from point A to B takes 24 hours, and then at specific time maybe the planet was at this point, and then it moves to that point, let's call them points C and D, and sweeps this area. So taking of course 24 hours as per his argument that the area and time are the same. So in case we have area 1 that is denoted by, let's call it capital M and capital M, where M denotes area, then Johannes Kepler's argument was that the line joining the planet to the sun, let's call this from point O. So line OA sweeps, when line OA moves to OB, it sweeps an area that is denoted by M in 24 hours. So in this case, when it moves from point, any specific location and in this particular orbit, when it moves from C to D, within the same 24 hours that it had consumed in this part of maybe just orbiting, then it will sweep out an equal area that we have denoted like that. So Johannes Kepler's argument, together with other concepts that have been employed in trying to find areas of some figures, of course we have talked about regular figures, like symbol curves and parabolas. The symbol curves, like the one I've just demonstrated, and then parabolas. So there were some specific concepts that were trying to be advanced in trying to find areas, of course, under the curves, and some of the parabolas led to Isaac Newton, of course. So we talked about Newtonian laws, so led to Isaac Newton to discovery of a new method that was used to find, of course, these areas under the curves that was known as methods of fluxions. So Isaac Newton's discovery of the methods of fluxions is what led to the concept of calculus, of course. So in this case, the methods of fluxions, that aspect that was being referred to at that time, is what led to the development of the concept of calculus. Now, as we were saying about the area under the curve, we're going to see how the relationship works between this, of course, the area that we're talking about, and the functions and the terms we had introduced before. So that was a slight, of course, connection between the works that were being done earlier by mathematicians and scientists trying to find areas beneath the curve. So let's look at this concept of area beneath a curve. Now that we're going to refer to as an integral. So in that case, I'm just going to do a rule for demonstration and try to see how this one works out. So suppose we have this graph like that, and then we have got a curve. Of course, we shall give you a function for that curve. Now that we've talked about the term or the definition of a function, from point A to B, and then this is f of x, and this is the origin. So in that case, of course, the area that is bound between A and B in this particular graph, this of course this is a one-dimensional graph. It's along the x and y axis in the normal Cartesian plane that we talk about. So the area under this curve, of course, will give us the concept of the integral, now that we talked about f of x as a function. So in this case, we needed to find a notation to describe this area that is beneath the curve that we are referring to as an integral, which will give us a description. Now, if a function fx is continuous, now if a function of fx is a continuous one, and of course which is a positive over the domain, positive refers to, of course we talked about this Cartesian coordinate. I hope that we are conversant with it about the negative and the positive aspect. So in this case, the motion along the x-axis in the positive direction is indicated by that. I just indicate using this red, that the motion along the x-axis and the y has a movement in the positive direction, just to give us a clue. So in this case, if a function fx that we've noted is continuous over the positive side, of course, which we have said, and over the domain, which means this A, this bound for A, because I hope those symbols we are familiar with them. That one refers to as equal or greater than, if x, because they say this along the x, if x A, of course x is equals or greater than A, or x is smaller than or is equals B, that one gives us a bound for this restriction for the point A and B, which means it is the area between A and B that is being referred to. We call the area beneath its curve the integral of fx from x is equals A to x is equals B. So this area is referred to as the integral of fx from A to B, as I've said. Now for us to give a bit an annotation, then we'll use this term and say that we have defined this one in its definition of terms. So this one, area that is beneath the curve, will be given as the integral of fx from x is equals A to x is equals B. Of course, this will be the domain for that integral. So the symbol, this one is an elongation of the term x that is used to refer to as the sum. Of course, this concept of the sum comes from the point that if we try to split this area that is under the curve into small rectangles, you'll find that of course there will be some slight areas which are emitted on this side and others added on this side, so they cancel out. So if we try to divide the area that is under the curve into small, of course approximately like rectangular strips, we have said that from definition of a rectangle, it's a regular figure which appears like this, and we say that this one can be the width and length. So that's how we find the area of that regular figure that we refer to as a rectangle. But in this case, since we have been given the denotations for the function and x, so the variation along this x-axis will be given for a rectangle. We said a small increment can be given as using this sigma x. So the change from this point to this one will be sigma x, and if it is they all change across this stretch here, then it will be given as dx, of course, which is the total change in the x direction. And then, of course, the change in the y-axis will be given as fx, which is a function we have said, and therefore area of that particular, the totality of the areas of the rectangles that is given there will be given as length times, of course, the total width that we have talked about. So that's fx dx. So that is why we are trying to say that the area under the curve is a summation from A to B of the rectangles, which are made, of course, of the length, individual length, and of course the height for fx. So that's how the concept of calculus came by. So let's try to look at one of the symbols, explanations that we can use in order to try and figure out how this concept works. So suppose we have another graph there, and then we have a function which of course we can just give us fx, which is 2x plus 4. So if this fx, we're trying to give out this as 2 changing by a factor of 2, this is 6, 8. And then we have this 1, 2, 3, 4. It's along the x and y, of course, which you have given us fx. So suppose we have a area under the curve that of course appears like this. So we realize that this is a regular figure, of course. We talked about, I hope I'm correct, that's a trapezium. So the area of this one that is bound by this is given as A equals a half AB, a half A plus B H. So that will be the area that is bound by that particular figure. So in this case, if you try to do a normal calculation for this area, we should find that the difference between this one and this point is 8 units, and then from this point and this one is 6 units. So these are the commonly points that I refer to as A and B. So we'll do a substitution for that and find that is 6 plus 8 into the H. The difference between this one and this one that we were just calling the sigma x is just 1 unit. So this is a 7 square units for the area that is bound by that curve. So in that case, of course, if we had a function like this that I've written on the board, so that area is 7 square units. Suppose we had a function like this, we shall look at different methods that are used to do integral functions. But for this, we can look at this and say that simply it's done like this is 2. Of course, it's an integral of this function f of x, which is 2x plus 4 dx from, now this one will be from 1 to 2, the one that we say the variation of x. So in this case, we just do an integration of this and then find this is 2x squared plus 2x over 2 squared. And then we've got another one, which is plus 4x. Of course, we're going to do a substitution for that. So different methods of integration, but for this, I just do a summary for the sake of our time. I see that here. So for that case, find that the area under this curve for the function f, this is fx 2x plus 4, is an integral for this. So we do the calculation, that is x squared over 2 plus 4x. And then we do a substitution for 2 to give us 12 minus a substitution for 1, it will give us 5, which will give us 7 square units. So if we find the area of a trapezium, as we had said, and then using the integration method, we just find the same. So that's a relationship in that integral calculus. This concept can assist us finding areas under the curve. So for that case, this is it for today, guys. So thank you, and we shall be doing other examples which are going to complement on this. I hope that this concept is going to assist us in advancing other concepts that we're going to find, which are subsequent ones in the topic of calculus. So without further ado, thank you and welcome. Bye. God bless you.